In my session yesterday, we started to look at the idea of control flow, how you're executing statements in a certain order, and how if you use similar statements but change the order of execution, you can achieve quite different results. We used the example of trying to crack a safe, trying to break a combination lock. And we set up a lock that had 2 digits from 0 to 4 and found that typically to crack the first digit and then guess the second digit overall together took about 5 guesses. Today we're going to subtly change that problem while also focusing on a combination lock to make the problem more like how you would have to try and crack today's passwords, which is to guess them all at once instead of, as with an old world safe, having to crack one digit and then the next digit. In setting up this problem slightly differently, we're going to see that we can achieve different results with very similar programming statements. This particular session focuses, in terms of the Wyoming computer science domains, on all aspects of algorithms and programming. It also touches on data visualization as a part of data analysis, and it even touches a little bit on cybersecurity. Before we discuss today's problem, as this is the last session of the week, I want to focus a little bit on some of the terminology I've been using through the week. I've discussed information, computation, and automation in depth. And I've also used the phrase logic and recently in the last couple of days, control or control flow to discuss a program. To reiterate what these concepts are, information is usually your input to a program. This could be drawn from the world itself. In the first session of the week, we actually used things like detecting temperatures or detecting light levels to bring information into your microbit. In the problem we were considering yesterday, the combination lock, your information is simply your input, which is a random number chosen by the microbit. Your computation, I focused early on the week on if-then logic statements, the green blocks. But you can really think of computation as everything that happens in a computer program between your information, between your input and your results, here when we plot the guesses to the screen. So it's not just if-then statements, decision-making logic that corresponds to computation. It can be anything else in there. For example, all the way back in on day one, we took a number in degrees Celsius, we multiplied by 9/5 and added 32 to turn it into degrees Fahrenheit. That calculation was part of the computation as well. So computation is really anything between your inputs and your results, all of the magic that computing can carry out. Automation is another concept I've discussed. Automation usually involves loops. If in the combination lock problem, instead of pushing button A 4 times, I'd asked you to insert a loop that said, okay, while I haven't got the right answer, while guess 1 does not correspond to lock 1, while guess 1 does not equal lock 1, let's just keep going. Let's keep generating guesses and guesses and guesses and guesses. You could think of this like a computer algorithm trying to crack a password. It's really, really difficult for a human being to sit and type words over and over and over and over again. You're never really going to crack a password unless it's a really bad one like hello or password 123. But a computer would have little difficulty scanning through lots of letter and number combinations in a loop to try and guess the password. In this problem, you could put it in a loop, press play on the program, and almost instantly it would come up with the correct answer because it's not going to take many times through a loop, much automation, to guess a couple of numbers between 0 and 4. Strictly, if you're pushing the button all the time, we haven't automated the problem, but we could put this while loop in there, let the microbit run forever and ever and ever, and the problem would be automated. Finally, I've discussed logic. Logic statements are things like if and then. We've had ands if something is equal to something and something else is, or something else is. If then, else statements, which we've also discussed. Those are logic statements. And the overall control flow is the way that statements are executed. And in this problem, I want to highlight control flow a little bit more by demonstrating how important it is how important it is that you choose a correct order in which to execute your statements. And to do that, we're going to change this problem very, very slightly. You're going to use similar statements. You're going to use a similar setup to yesterday for my combination lock problem with lock 1 and lock 2 guesses, guess 1 and guess 2, and you're going to plot things to screen. But yesterday, here's the problem setup. I asked you to have a problem where you pushed button A until you broke the lock for that particular column. It's going to take a while, I guess. And then once you've done that, you pushed button B. And I asked you to work out how many times you would have to push A plus B to break the lock. Pushing A and then B, breaking the first column, the first digit of the lock, and then the second column, on average, it takes 2 to 3 times to guess this. Column 1, lock 1, corresponding to number lock 1. And on average, it takes 2 to 3 times to get lock 2, the second digit. And so overall, it takes about 5 guesses. We're going to change that around in this problem. Today, instead, I want you to set up a lock where when button A is pressed, you guess both lock 1 and lock 2 simultaneously. The problem that you set up yesterday for the combination lock, guessing A first, and then once you get A, guessing B, is sort of like if you've seen an old movie where somebody is cracking a safe, they have a stethoscope, and they lean down and they put the doctor's stethoscope up against the safe and they turn the lock and they hear a click when they've got the first digit. And then they keep going and then they hear a click when they've got the second digit. So you're allowed to guess 1 and then 2. That's not really how a lot of password cracking or digit cracking or PIN number cracking happens these days though. Mostly people will try and guess it all at once. You'll have to guess here 2, 0 simultaneously. You'd have to guess 20. You wouldn't be allowed to guess 2 first and then 0. So the challenge for today is to set up a lock where you have to guess both the values of lock 1 and lock 2 simultaneously. So every time button A is pressed, you're going to guess both lock 1 and lock 2. As with yesterday's problem, if you guess correctly, display the correct digits in column 1 and column 2 of the microbit LED display. My question is, yesterday it took 2 to 3 guesses for A, 2 to 3 guesses for B on average, for a total of about 5 guesses. Today, if you're guessing both simultaneously, instead of guessing A and then B, when you push button A, if you guess both simultaneously, how many times do you have to push button A to guess both all at once? You're going to use basically the same statements as yesterday. You won't be pushing button B at all because pushing button A is going to generate both guesses. And leadingly over here, you will need to use one of these AND logic statements, which means that if something is true and something else is true, then you execute some action. So that's the main goal for today. Once you've answered the question, how many guesses on average does it take to break this version of the lock where you have to guess both columns at the same time? A stretch goal, because it can take quite a while to break this version of the combination lock, a stretch goal for today is as follows. Instead of only lighting up the LEDs when you guess the right answer, as we do here, nothing lights up until we guess the result for A and guess the result for B. So instead of only lighting up LEDs when you guess the right answer, light up the LEDs showing you what was guessed every single time you push button A. And then, after about a second, unplot these LEDs. You'll notice that in the LED display, there is an option both to plot the LEDs, but also to unplot them, to remove them from your plot. So, display the guess every single time, not just when it's right, and unplot it after 1 second. And then you'll push button A again and another guess will appear. When you've guessed the correct answer, light up the correct answer in columns 3 and 4, which correspond to 0, 1, 2, 0, 1, 2, 3 in this plot XY command. So those are the tasks for today, and I'll get back to you in about 30 minutes with the solution to this problem.